thank you to the organizers for the invitation. So it's a pleasure and honor to speak on this occasion. It would have been nice to come to Cordoba. I hope we can do this in the future. So I will speak about metric cones over semi-Riemannian manifolds. So it is mainly about joint work with Thomas Leisner and Dmitry Alexeyevsky. So Thomas is also one of the participants of this meeting. He could not come this morning, but he will be here later. So let me start with the definition of what is a metric cone, which is the principal object of study for this talk. So we start with the semi-Riemannian manifold Mg, and then a metric cone over M is a manifold of the form, the product of the positive real axis times the manifold M, endowed with a warp product of the following form. So it's up to a sign epsilon, which is plus or minus 1. It is dr square plus r square g. And in the first case, when epsilon is plus 1, one speaks of the space-like cone. And in the second case, for epsilon minus 1, one calls the cone the time-like cone. In fact, in this setting, there's no principal difference between time-like and space-like cones, because you can multiply the cone metric with an overall minus sign, and then you can pass from one type of cone to the other type. But nevertheless, it's sometimes convenient to fix the case you are considering, because, for instance, the base may be positive definite and you don't want to change it to negative definite, for instance, or it may be useful if you fix some signatures to say precisely what is epsilon, but in principle it doesn't matter. So let me give you a basic example which you all know. So if we consider a manifold of constant curvature epsilon, so plus 1 or minus 1, then the cone, which is defined here, will be flat, where epsilon is exactly the epsilon here in the cone metric will be exactly the curvature, constant curvature of the base manifold. In fact, this is a fact which is very easy to show, and it follows from the curvature formulas for such type of warp product for these cones. And perhaps it will be helpful to recall some of these formulas very briefly, only the most important ones. So I have another application open here, so I hope I can just write here on the iPad. Okay, so here I have a blackboard, and we can now recall some formulas for metric cones. So if M hat is a cone over some pseudo-Riemannian manifold M, then you have very nice formulas for the Levi-Civita connection and for the curvature of the Levi-Civita connection. So for instance, if we denote the Levi-Civita connection on the cone by nabla hat, and by nabla the Levi-Civita connection of the base manifold, then, for instance, you have such type of formulas for vector fields on M. So every vector field on M can be canonically considered as a vector field on the cone M hat. And for such type of vector fields, the covariant derivative of the cone is related to the covariant derivative in the base manifold by this type of formula. In fact, now it depends on what I chose here for epsilon, but it is not very essential here. So we have here minus epsilon g of x y times psi. So you have such simple formula. And from this formula, you get nice formulas for the curvature. So also you can differentiate the Euler vector field. So you have the tangent bundle of the cone, which you can decompose into the line spanned by the Euler vector field plus the tangent space to M at every point. So psi is here the Euler vector field, which in the case, if you write the Euclidean space as a cone over the sphere, then it's just a position vector field. So you have such type of splitting, and the covariant derivative of this Euler vector field is exactly the identity. So this is, in fact, the practically the only equation you need to remember when you work with conical metrics. So this is the local, so this equation locally characterizes a matrix which can be written as a metric cone over some other manifold. So we have the covariant derivative of psi is the identity. So this is a homothetic Killing vector. And from these formulas for the connection, we get the simple formulas for the curvature. So for instance, if we denote the curvature of the cone by r hat, then we know that whenever you plug in the vector field psi, the Euler field, into r hat, you get 0. This can be easily checked. And for vector fields on the base manifold, the curvature of the cone is related to the curvature of the base manifold by a rather simple formula. So this is equal to the curvature in the base plus some expression which looks formally like the tensor of constant curvature based on the metric G, which is the metric on the base manifold. In fact, here this plus will be a minus epsilon. So for epsilon equal to -1 is plus. So minus epsilon, and then we have G of y zx minus G of x z y. So we see from this formula, we can check immediately that if the base manifold has constant curvature epsilon, then these two terms cancel. So if you take here curvature tensor of constant curvature epsilon, then the curvature of the cone would be 0. And you have also formulas for the Ricci curvature. So Ricci of xy is equal to Ricci of the base manifold. So here always x, y, z are vector fields tangent to the manifold M minus epsilon n minus 1 G xy. Okay, so from these formulas you can check various things. So for instance, one consequence is that that such a cone can only be Einstein if it is Ricci flat. So this is a general property which you will use later in the talk. Okay, so after having recalled such formulas, which are very useful for orientation here, I continue here with the Beamer presentation. So as we saw, if the base manifold has constant curvature epsilon, then the cone metric is flat, and this is if and only if, at least if the dimension of the base is larger or equal to 2. And we will be interested in studying the holonomy of such cones. And there's an important distinction from the very beginning. You can study cones which are decomposable and cones which are indecomposable. So at least you can ask the question whether you can decompose the holonomy representation as a sum of two sub-representations with the property that it is a sum of two non-degenerate subspaces, so orthogonal and orthogonal to each other. And if such decomposition is not possible, then you call the representation indecomposable. So this may look a bit strange for you because you know all the notion of irreducibility for representations of compact groups, for instance. But here, since the metric is not a positive definite, we cannot assume that our representation is completely reducible, so it's not necessarily a sum of irreducible representations, but what is always true is that it is a sum of indecomposable subrepresentations. So you can split your representation space as a direct orthogonal sum of sub representations which can no longer be split into smaller subspaces. Okay, so so we call the manifold indecomposable if this representation is indecomposable. So I recall that the holonomy group, perhaps I use the blackboard here to show this. Okay, so I briefly recall what is the holonomy group. of a pseudo-Riemannian manifold. So this group is obtained as follows. You have your manifold, you fix a point in the manifold. Of course, we assume that the manifold is connected. You fix a point, and then you consider curves with base point P. So they start and end at the point P. And you have the parallel transport along such a curve, and this defines some orthogonal transformation of the tangent space at the point P. And these transformations generate a group, and this group is called the holonomy group. So you can define this for every connection, in fact, and in particular for every semi-Riemannian manifold. You have the holonomy group, and its Lie algebra is called the holonomy algebra. So it's a Lie algebra of the holonomy group. And so this holonomy group encodes many interesting properties of a pseudo-Riemannian or semi-Riemannian manifold. I'm using the two terminologies equivalently. So for instance, you can see from the holonomy group whether you can decompose whether there exists, for instance, a parallel distribution on your manifold. This would correspond to an invariant to a subspace in the tangent space, which is invariant under the holonomy representation. Okay, so let us return to the slides. Okay, so this indecomposability means geometrically precisely that you cannot write the manifold locally as a product of two semi-Riemannian manifolds with a product metric. So this is not possible if a manifold is indecomposable. And then the main result about Riemannian metric cones, so due to Gallot from 1979, is that a Riemannian metric cone over complete Riemannian manifold is either flat or indecomposable. In fact, in that case, you can just say irreducible, because it will be the same in the positive definite setting. And this was a very useful, I mean, it is a very useful theorem, because you can immediately apply Berger's classification of irreducible holonomy groups. So if you study such a cone, and then knowing that the base manifold is complete implies already that the cone will be either flat, in this case, of course, not so interesting, or it will have automatically irreducible holonomy representation. And then you can look up all the possibilities in Berger's classification of irreducible holonomy groups of Riemannian manifolds. And for instance, this was used by Christian Beer in his classification of manifolds with killing spinors. So he translates the property of having a killing spinor into the property of having a parallel spinor on the cone. So killing spinors on the base manifold correspond to parallel spinors on the cone, and of course parallel objects like tensors or spinors correspond to invariants under the holonomy representation. And if you know all possibilities for the holonomy groups, you can study and answer this question. This is exactly what Christian Beer, building on previous work by various people, did, and so he was able to solve this problem. Okay, so we will be interested here not in the Riemannian case, but in semi-Riemannian metrics. And so the first question is whether such a theorem holds for semi-Riemannian manifolds. So whether the metric cone over semi-Riemannian manifold is either flat or indecomposable. And it turns out that this is in fact not true. So the Gallot's theorem doesn't hold for semi-Riemannian manifolds. So it's an example of the general fact that not every statement which you can transport from Riemannian to semi-Riemannian manifolds will be true. So in some cases, things fail. And here, this Gallot's theorem fails in the semi-Riemannian setting. And here's an example, so a counterexample. So if we consider some arbitrary complete semi-Riemannian manifold F with a metric GF and assume dimension is at least 2, and which is not of constant curvature 1 to exclude the flat, which is not of constant curvature 1, then we can consider this particular warped product, so minus ds squared plus hyperbolic cosine of SGF. And you can check that this metric is complete. So in fact, you can show that the geodesic equation has complete solutions. So solutions are defined for all times using the property that the metric on F is complete. But nevertheless, it turns out that the cone over this manifold, in fact, we consider space-like cone, is decomposable and non-flat. So this can be checked by showing that if you take the distribution defined by the tangent bundle of F together with a particular linear combination of the vector fields d over dr and d over ds, then the span of these two of this vector and of the distribution Tf is in a parallel distribution, so invariant under the holonomy. It corresponds to a subspace invariant under the holonomy representation, and this is a non-degenerate subspace. So this means that that the cone is decomposable, and you can also check that it's not flat. In fact, here the F is particularly an arbitrary Riemannian metric, so you can easily check that this is not flat. So this gives a counterexample. So you could, at this stage, abandon the topic and say, okay, it doesn't work, and so what can we do? But in fact, it turns out that if you add some stronger condition, so completeness is not sufficient to obtain the Gallot theorem in the semi-Riemannian setting, but we found that adding a stronger assumption, you can still prove the Gallot theorem, and this stronger assumption is compactness. So if we add to the statement of the Gallot theorem we state it now in the semi-Riemannian setting, but we add the assumption that the base manifold is not only complete, but we want it also to be compact, then the same assertion as in the Gallot theorem is still true, and the manifold is either flat or indecomposable. So here we used, in fact, both properties, so both hypotheses, completeness and compactness, are included here because for semi-Riemannian manifolds, it's not true that the compactness implies the completeness, so we included both assumptions, and under these assumptions, in some old collaboration with Dimitri, Anton, and Thomas, so Anton Gallot, we showed that Gallot's theorem remains true if we have a compact, complete semi-Riemannian base manifold. And in fact, this result was later extended by Matveyev and Monod. So they showed that they assume compactness as we do, but they could get rid of the completeness assumption. So in fact, this theorem can be proven with compactness alone. So I think this is the state of the art now. It's from 2010, so it's more than 10 years ago. And we also described the structure of decomposable cones. So we saw in the previous theorem that the cone will be indecomposable if the base manifold is compact. But if it's not compact, then there can be decomposable cones over complete manifolds, and we have a structural result for this case, so which is here. So we assume that M is a complete semi-Riemannian manifold of dimension at least 2, and we consider a space-like cone and assume the cone is decomposable. Then the question is, what can you say about the base manifold? And we prove that on a dense open subset, the base manifold can be decomposed in components, open components, and each component is either of constant curvature 1, in which case the cone over this part will be flat, or it is of this special form 2. So it is such a double warped product over a line with warping functions sine and cosine, hyperbolic sine and cosine. And here G1 is an completely arbitrary pseudo-Riemannian, semi-Riemannian manifold. So G1 is arbitrary, but G2 is special. So G2 is of constant negative curvature, -1, or of dimension less or equal to 1. So this type of double warp product generalizes the example which I gave before. So in the example which I gave before, the second term with the hyperbolic sign was not present, and we had only this first term. But more generally, you can add this term with the metric G2, and this is the most general possible form for the base manifold of a cone which is decomposable. So this is a local result that you have such decomposition. So you have a dense open subset, and each component of the dense open subset is of this form. And again, this was studied further by Monod, and he could improve the result as follows. So in fact, you can show that under our assumptions, M has either constant curvature, or the universal covering of M is of the form 2. So it's a stronger statement than just assertion that you have this open dense subset, but in fact you have all of the manifold is of the form 2 up to passing to the universal covering. Okay, so the next thing which I want to discuss is our more recent work. So so far this was a work 10 years ago where we started to look at this problem together with Dimitri, Anton, and Thomas. But more recently, we published a new paper in this subject where we study the indecomposable case. So we do now describe the possibilities for indecomposable cones rather than studying the decomposable case. So we consider an indecomposable metric cone, M hat. And the claim is that there are two cases. Either it admits a parallel totally isotropic distribution locally, or it has irreducible holonomy algebra. And then this holonomy algebra is from this relatively short list. So I can illustrate a little bit this list. So in the first item of this list, we have the holonomy algebras of orthogonal type, so the algebra SOTS, but also the complex orthogonal Lie algebra SONC, which you can realize a subalgebra of SON, N. So for neutral signature, this can occur. Then in the second list, we have a rather interesting special case of holonomy algebras. They all correspond to semi-Kähler or pseudo-Kähler geometries. So this holonomy U, P, Q exactly means that the metric is of Kähler type. So you have a parallel complex structure, which is skew-symmetric for the semi-Riemannian metric. And SUPQ corresponds to Calabi-Yau, to the pseudo or semi-Riemannian analog of Calabi-Yau, of the Calabi-Yau condition. So Ricci-flat pseudo-Kähler or semi-Kähler. So which is these are subalgebras of SO2P 2Q. And the third case corresponds to hyperkähler, semi-hyperkähler type of geometries, where you have three complex structures, J1, J2, J3, which behave like the unit quaternions IJK, so they have the same algebraic rules. All three are parallel and skew-symmetric for one and the same metric. And finally, you have these somewhat exceptional cases 4 and 5, so they are related to exceptional geometries of type G2. So you have the compact, the Lie algebra of the compact group G2, but you have also the non-compact form, which is called G2-2. It is a subalgebra of SO 3,4, so signature 3,4 in 7 dimensions. And you have here also this complex version which lives on a 14-dimensional manifold of neutral signature, and similarly for spin 7. So we have spin 7, so you have spin 3, 4, and finally you have the complex form of spin 7 considered as a subalgebra of SO8, 8. So this is the full list of possibilities for the irreducible holonomy algebra of a cone. So I would like to very briefly explain how this classification comes about. So in fact, it's not so complicated as it may seem, because we can build on existing work. So first of all, you can distinguish two cases. Either the holonomy algebra is reducible or irreducible. If it's reducible, this means that there's an invariant subspace in the holonomy representation, and this subspace is necessarily degenerate, because we are assuming that the cone is indecomposable. And this means that there is no non-degenerate invariant subspace, no proper non-degenerate invariant subspace, but there can be degenerate subspaces. And so if you have such degenerate subspace, then you can take the intersection of this subspace with its orthogonal complement, and this will be a totally isotropic subspace invariant under the holonomy representation. And then you can, by parallel transport, you can generate a parallel totally isotropic distribution on your manifold. So this is the first case. It's in fact stated here. Then it either admits locally a parallel totally isotropic distribution, or the holonomy algebra is one of these. And the second case is this irreducible case, when the holonomy algebra is irreducible. And in that case, we can resort to Berger's classification of irreducible holonomy algebras of semi-Riemannian manifolds. So everybody knows that Berger classified the holonomy groups of Riemannian, so say irreducible holonomy groups of Riemannian manifolds, but he also classified the irreducible holonomy algebras of semi-Riemannian manifolds. He didn't classify the indecomposable ones. This is a more difficult problem, but he classified all the irreducible ones. And so we can use his list. But it turns out that this list here is shorter than the Berger list. So we excluded some cases from Berger, and I can explain how this comes about. So for instance, you may remember from the Riemannian setting that there's a holonomy group which is called SP1 times SPn. So perhaps I use a blackboard for that. Okay, so in the classical Berger list for holonomy groups of Riemannian manifolds, you find one very interesting group, which is usually denoted SP1 times SPn. And this group acts naturally on R4n, which you can consider as the quaternions to the power n. This SP1 denotes the group of unit quaternions acting on Hn. So this Hn, you can think of it as some kind of quaternionic vector space. In fact, it's a module over the quaternions. And SPn is the subgroup of the orthogonal group which commutes with this quaternionic multiplication. So this is the group SP1 times SPn, and it defines a so-called quaternionic Kähler manifold. So Riemannian manifold with this type of holonomy group or holonomy subgroup of this group is called quaternionic Kähler. And such manifolds exist also in the semi-Riemannian setting. And in that case, you replace this SPn by a non-compact form of this compact group SPn, of the complexification of this group. And so you obtain, for instance, these groups SP1 times SPk, L, where this k, L indicates that on Hn you have chosen some indefinite Hermitian metric. So you could indicate this in this form. And this is a perfect irreducible holonomy group of semi-Riemannian manifolds, so it can occur, but it cannot occur for cones. And the reason is that this kind of holonomy implies the Einstein equations with non-zero scalar curvature. But as I said, the cone can only be Einstein if it's Ricci flat. So this means that these groups do not appear. And the remaining ones in the list, they can be all realized by semi-Riemannian metrics. Okay, so that's how we obtain this kind of result. So it's builds heavily on Berger's very important classification of irreducible metric holonomy, so irreducible holonomy groups of torsion-free metric connections. And now, so as you saw in the previous theorem, there are two cases: either the so for an indecomposable metric cone, there were two cases: either you have irreducible holonomy, or there's an invariant null line. And now we want to study this case when there's an invariant null line, a parallel one-dimensional rank 1 distribution on the cone. So we consider now a cone M hat with a parallel null line. So we take the time-like cone, but okay, this is just we fix the ideas by fixing here the signature. This epsilon will be -1. So consider time-like cone with a parallel null line, and then what we show is that there exists some dense open set on which the metric is of the following form, of this form 3. So it is of the form 2 du dv plus u square g0 for some semi-Riemannian metric G0. So this 3 is the metric of the cone. So in some sense, it's a normal form for the metric of the cone if you assume the existence of a parallel null line. And you can also describe explicitly the metric of the base manifold of the cone, which was called G before. And this metric will be of the form ds square plus e to the power 2s G0. So it's a warp product. And again, the metric G0 appears here. So this is some local classification of such cones with parallel null lines. So they are all of this form. And conversely, if you start with an arbitrary metric G0 and consider the warp product G, then the cone over this warp product will be isometric to this metric G0 tilde, and will admit a parallel null line. So it's if and only if. So we have complete local classification of such time-like cones with parallel null line. And I want to explain a little bit how this is obtained. Okay, so perhaps I leave it a moment for you to read the full statement. So we want to show that every cone with a parallel null line is of this form 3 for some metric G0. And conversely, if you have a metric G0, if you start from a metric G0, then we want to show that the cone over this metric G, defined as a warp product, is a cone with a parallel null line. Okay, so one part of this statement is rather easy to prove. So if we start from the metric G, which is ds squared plus e to the power 2s G0, then you can consider the cone metric and just check that it's globally of the form G0 tilde. And for this, you have to construct an isometry from the metric on the cone metric, and this metric G0 tilde. And here's an explicit isometry. So on the cone, you have the variable r, the radial coordinate. And on the manifold M, you have the coordinate s, because M was a warp product with s as a warping, or e to the power 2s as a warping function. And P denotes just a point on the manifold M0. Yeah, so P is just a label for M0. And then you can transform the variables R and S into new variables U and V, which are defined in this way. So U is R times e to the power S, and V is -1/2 R to the power e minus S. And then you can compute the cone metric in these new coordinates u and v, and you find that it's exactly of this form g0 tilde. And also you can check that it has a parallel null line. In fact, the parallel null line is spanned by the vector field d over dv. So you can check that d over dv from this form. It's immediate to check that this is a parallel null vector field, and so you have the parallel null line. Okay, so this proves the converse statement of the theorem, but still we have to prove that starting from some arbitrary cone with a parallel null line, it will be of this form. So, and there I sketch the proof. So to show that every cone with a parallel null line is locally of this form, we proceed in several steps. So first we show that the null line L is not only parallel, but it will be flat. So it's not only invariant under parallel transport, but the curvature of this one-dimensional bundle is 0. And this can be checked using the curvature formulas for the cone, because you can compute the curvature using the Levi-Civita the connection on this line bundle is induced from the Levi-Civita connection. So you can use the simple formulas which I showed to compute it. And you find by some arguments that it will be that the curvature is 0. So this means in particular that you have parallel sections of the bundle L. And so we may assume that our manifold is simply connected because we are proving a local statement. And then we have a global parallel section of the line bundle L. And so this is this section which I call chi here. So we have a parallel section of the line bundle L of this parallel null line. And by some calculations, again using formulas for Levi-Civita connection, we were able to show that this parallel vector field can be written in the following form. So it's, first of all, it's clear that it will be a linear combination of psi and some vector field which is tangent to M. But it turns out that it has you can extract the factor 1 over r, and what remains will be some coefficient f, some function, and some vector field z. But these tensors f and z will be tensors on the base manifold M. So it's not obvious, but you have to check this calculating the Lie derivative with the Euler field. So you compute the Lie derivative of chi with the Euler field using that the torsion of the Levi-Civita connection is 0 and the formulas for the connection. And then you can show that the coefficient of over psi of the vector field chi, of this parallel vector field chi, is of the form 1 over r times f, where f is a function on the base. And also you show that the tangent part will be up to rescaling with a factor 1 over r will be vector field on the base manifold. And then you can study, then from this form, you can try to extract some information about the metric. And you can extract this information on the set where the function f is non-zero. So this is a set which is open, and we show that this set is dense. So we have this regular part of M, it's a set where f is not 0, and it can be shown that it's not only open, but it is dense. And on this set, the metric, again calculating some Lie derivative of g in direction of psi, you can arrive at the end at this expression for the metric. So the metric g is ds square plus e to the power 2s times g0, where g0 is some metric on m0. And the function s, the warping function, is related to the function f, which appears here as a coefficient of chi, is a logarithm. The relation is that s is the logarithm of absolute value of f. And g0 is a metric on the level set s equal 1. restriction of the metric G to the level set S equal 1. So in this way, we obtain this normal form. So we really start from this parallel line and decompose a parallel section of this line into some components, and then from this function f, basically we extract the warping function in the expression for the metric. Okay, then we study also the holonomy of indecomposable cones. So we are still in the case of an indecomposable cone with a parallel null line. So this is an interesting case. So in the case of irreducible holonomy, this is understood by Berger, and we study now in the case of indecomposable cones, which are reducible and have a parallel null lines, so still in the setting. So the question is, what can we say about the holonomy algebra of such cones? And okay, first remark is that we will now specialize a bit, because the case of general arbitrary signatures is complicated, and we will restrict to the case when in this normal form obtained from a metric, auxiliary metric G0 on some auxiliary manifold M0, we assume that G0 is Lorentzian, and this means that the cone will be of index 2. So we have an indefinite cone of index 2, and the metric G0 is Lorentzian. It's a Lorentzian metric. Okay, and in this setting, we have the following. So if we start from a Lorentzian manifold M0 G0 and consider this particular type of double warping, M0 tilde equal R positive times R times M0 with the metric G0 tilde, which is written here. I mean, it's a warp product where this part UV is two-dimensional, and we assume that this manifold is indecomposable. So recall that this was exactly the normal form for the cone. So the cone metric is of this type, and we assume it's indecomposable. Then the result is that the holonomy of this metric, G0 tilde, is related to the holonomy of the metric G0 by this formula. So it's holonomy of G0 tilde is a semi-direct product of holonomy. I think here the semi-direct product should be in the opposite direction. So the ideal is the normal. Okay, the ideal is Rn, is the normal subalgebra. So we have a linear part, which is the holonomy group of G0, and the translational part, which is Rn. So this is a claim. Or if this is not the case, then the manifold M0 tilde admits a parallel totally isotropic plane. So we have either the case where we understand completely the holonomy algebra as such semi-direct product, or otherwise there exists a totally null two-plane. Okay, so this is some kind of classification of this case of cone indecomposable cones with parallel null line into two important subcases. One case where we understand the holonomy, and the case where we have a parallel totally isotropic two-plane. Okay, and in this theorem, we can also allow a G0 to be Riemannian. So it's a remark. So we are in our recent work, we study this Lorentzian case, but you may allow also the Riemannian case. And then the conclusion is that the holonomy is always such a semi-direct product, because in the Riemannian case, obviously there can be no null plane, so the second case is excluded. And we have this result about the holonomy algebra also in the case when the manifold M0 is Riemannian, and in that case the cone which we are considering will be Lorentzian. Okay, so it still holds. So I would like to sketch a little bit or mention some methods of proof. So the full proof is complicated and long, but let us at least mention some logic of the proof, some arguments. So the problem is the following. So we start with a semi-Riemannian manifold Mg. So now I drop the index 0. So you could write M0, G0, but for simplicity, we drop the index 0. So we have now semi-Riemannian manifold Mg, and we want to compute the holonomy algebra of the manifold M tilde, which has two more dimensions. Here R positive times R, and the metric is 2 du dv plus u squared times G. So this is a normal form for the cone metric of a cone which has a parallel null line. Okay, we want to compute the holonomy. That's the problem. Then we can use some general facts which are true in arbitrary signature and do not yet require Lorentzian signature for M. So first of all, the holonomy algebra of G tilde, I will abbreviate it abbreviated as Gothic G tilde here. It's a subalgebra of SOT plus 1 S plus 1, and it is related to the holonomy algebra of G as follows. So G tilde is, we don't know in general that it's equal to semi-direct product. Now I think I wrote it in the correct order. But it is a subalgebra of this affine algebra G semi-direct product with R, T, comma S, which sits inside of SOTS, semi-direct product with RTS. And this semi-direct product is in fact a subalgebra of SOT plus 1, comma S plus 1. It's a subalgebra which fixes a null vector V0 in the orthogonal complement of RTS inside of RT plus 1 S plus 1. So we have the big tangent space, which has signature T plus 1 S plus 1. In it, we have the tangent space of M, which has 2 dimensions less. And in the orthogonal complement of this RTS, we choose a null vector, and then the stabilizer of such null vector has this type of structure, SOTS, semi-direct product with RTS. So that's why this appears here, this affine algebra. And then we know a little bit more. So it's not just a subalgebra, but we know that if you project this subalgebra to the linear part, so to SOTS, or here in this picture to this G, then you obtain all of G. So it's some subalgebra, which when you take the quotient by the translations gives you the full algebra G. So this is these are general facts which are always true. And then we distinguish different cases. So we consider the translational ideal, which is the intersection of the algebra G tilde with the translations. And it is a priori, it's not clear what is this intersection. So there are different possible cases. But we could consider the case when this intersection is all of the translations R, T, comma, S. Gives a whole vector space R, T, comma, S. In that case, we obtain immediately that G tilde is such a semi-direct product. But in general, this T, this ideal of translations, could be smaller than R, T, comma, S. And the claim is that if it is smaller, then one can prove that G tilde admits an invariant null plane. So we are in this case of existence of a totally isotropic two-dimensional distribution, at least if the index of the metric G, so index is a T, a number of negative directions, of time-like directions, if it is at most 1. And also using the fact that G tilde acts indecomposably. So we are always in the setting that we have indecomposable cone metric. So the holonomy algebra G tilde is assumed to be indecomposable. And now we add the assumption that the index is not too big, so it's at most Lorentzian. Of course, if it's Riemannian, then there can be no invariant null plane, and this means immediately that you have such semi-direct product if our claim here is correct. So we are it's a claim. Okay, so how can we prove such type of claim? Yeah, so let us consider first the case when we have a Riemannian manifold M, which is simpler, just to get an idea of what is true. And okay, so if the manifold M is Riemannian, then we know that holonomy algebra will be the algebra of a compact group, and then it is completely reducible, so you can split your representations as a direct sum of irreducible representations. And in that case, the result here follows from the next theorem, which is a theorem only about this completely reducible case. So if we assume that the representation is completely reducible, then we have a special theorem, and this special theorem shows that the holonomy algebra is such semi-direct product. So this is on the next page. And later we will have to discuss also the case when it's not completely reducible. But for the moment, consider this completely reducible case. Okay, so in the completely reducible case, we have this theorem. So we start with a semi-Riemannian manifold of signature Ts with completely reducible holonomy algebra. This is an assumption. It's not always the case. And we assume that the holonomy algebra of the cone is indecomposable. And we assume also that the translational ideal T is non-degenerate. Under these assumptions, we can prove that the holonomy is such semi-direct product. And let me explain very roughly how this is proven. So we use that, we first prove that G annihilates the orthogonal complement of the translational ideal. It's not at all obvious, but we prove that G acts trivially on the orthogonal complement of translational ideal. So, and then we can distinguish two cases. Either T is all of the space of translations RTS, in which case T perp is 0, and of course then this condition here is trivially satisfied. But in this case, if T is RTS, we already know that we have this semi-direct product. In that case, we have semi-direct product, and we are done. Or if this is not the case, then we have a non-degenerate G invariant vector, because we can choose then in the space T perp some non-zero vector, which is non-degenerate, so not light-like, and this gives a vector invariant under the holonomy representation of the base manifold, and then one can show that if such vector exists, then there's also a G tilde invariant non-degenerate vector under the holonomy representation of the cone, so under this G tilde. And then we have the parallel null plane, because we have two independent parallel vectors. On the one hand, we have this vector field d over dv, which we always have for this type of matrix G tilde, so which spans the parallel null line, but we get an additional vector which comes from the existence of this G invariant vector under the holonomy representation of this G, of the algebra G. So this proves this sorry. So here in this setting, so we have this two-dimensional. It's correct that we have this invariant two-dimensional isotropic plane, but it's not totally isotropic because one of the vectors here is a non-degenerate vector, invariant under G tilde, but this means that G tilde is decomposable. If it has such invariant non-degenerate vector, then it's decomposable. But we assumed that the algebra G tilde is indecomposable. So this means that the second case cannot occur, and we proved the semi-direct product. And to prove that G vanishes on T perp, we use this next theorem. So I abbreviate a little bit to shorten the notation. So we denote V as RTS and V tilde is RT plus 1 S plus 1. Then we consider an indecomposable subalgebra of the stabilizer of a null vector, which we call G tilde, such that the projection onto the linear part is G, and such that this G acts completely reducibly, and such that the translational ideal, so the intersection of G tilde with V, is non-degenerate. So exactly the assumptions which we made above. Then under these assumptions, now in this abstract setting, without stating that these are holonomy algebras, so this is just about indecomposable linear algebras, a statement about indecomposable linear algebras, we prove that GT perp is 0. So this is exactly this claim here. And one can give even a more precise information. So one can then describe this G tilde, which is our model then for the holonomy algebra of the cone, as a semi-direct product of the translational ideal T and some algebra H phi, which is in fact the graph of some linear map from G to T perp. So there's some more precise description of the holonomy algebra, which I only give here for completeness. It's not needed for this argument, but it is a typical example of the type of methods which appear in our paper. Okay, now I would like to finish by discussing the general Lorentzian case when we do not assume that the holonomy algebra is completely reducible, because in general you cannot assume this. So we start with a Lorentzian manifold with a holonomy algebra G, and consider this G0 tilde with indecomposable holonomy algebra G tilde. Then we claim that a G tilde is a semi-direct product, or a G tilde admits an invariant null plane. So that's the theorem which we want to prove. And in fact, it suffices to show that if T is different from V, so if T is equal to V, then we have semi-direct product. So T is the translation ideal. If it's not the case, then it suffices to show that there exists a G invariant null vector, because then this null vector gives rise to a null vector in the cone. So for in the metric M tilde, in the metric G tilde. And then you get an invariant null plane. So now the vector here is really a null vector. Before we had considered some non-degenerate vector. The scalar product is not 0, but now we consider a null vector in this Lorentzian setting. Okay, we use some, I will just summarize this very briefly. So we decompose our algebra into some of indecomposable ones. This is a generalization of the Ram theorem, which is used here. And then there are two cases. Either this translation ideal is non-degenerate or degenerate. And for each case, we have different kind of proof. So in one case, we can again use the previous theorem, which is the completely reducible case. So this applies to the case when this non-degenerate subspace is of Lorentzian signature. In this case can be excluded. Or this non-degenerate subspace is positive definite. And then we can again distinguish two cases. Either the first summand, which is always of Lorentzian signature, this was V1, is irreducible, and then we have again completely reducible representation, and we can use the previous result about completely reducible case. Or it is not irreducible, and then we show then there's an invariant null line, and using some cohomological methods, we use that there's an invariant null vector. And then the last case is when the T translation ideal is degenerate, and also in that case, we show that there's an invariant null vector. So, but this is really very brief summary. There are some non-trivial arguments involved in showing this. And so the last part is about cones with a parallel null plane. Unfortunately, I have not the time to go into details. I only show you the type of formulas we obtain. So if you have a cone with a parallel totally isotropic plane, then you can show that there exists on the base manifold two vector fields, V and Z, satisfying a system of differential equations. And in fact, this is if and only if. So to have a parallel null plane on the cone is the same as having on the base manifold a solution of this system. And okay, let us skip this. And we were able to solve completely the system. So we can describe the general solution of this system of differential equations. And it can be cooked down in coordinates to this system 8. And then it can be solved. So this is the solution of the PDE system. So which describes all metrics, if you like, for which the cone has a parallel two-dimensional totally isotropic distribution. So then I stop here since I'm over time. So thank you for your attention and patience.